cover functions. I'm going to draw some functions, and I'm going to start with sine, because sine and cosines are going to come up an unbelievable amount. We're going to review a lot of trigonometry in the process. This trig is going to come up a heck of a lot. For those of you who were not able to do the quiz on the sine question, or also to remind you, I think a lot of you need a reminder on some of your trig. Let me do a, oops, that's not good. Let me just start with examples with trigonometry. And so this is clearly a sine function, where this is pi, this is 2 pi, this is pi halves. So this is f of x is sine of x. And the derivative, therefore the derivative, which is of course the slope of this function. Let me remind you of how this works, and especially this is how you could have answered that question on the quiz where I drew a different wave function and said, hey, what is this? And the answer was cosine. Here's how you could have done that. Also to remind you, if you get stuck, if you have to do a derivative of a trigonometric function, if you try to remember it but you're not sure, this is how you get out of it. Now, so remember that derivatives are oh, here, let me actually cover, what a derivative really is. A derivative is technically, and I even forgot this myself, it's technically defined as a limit, which it defines a slope, but this is the actual limit. It's when you take a infinitesimally addition to the right of the function, subtract to the left, and you let that difference go to 0. Yeah, this is what a derivative is technically. This part, so it's not too hard to see that the reason we use this language is that this bottom part ends up being called a differential, and this top part is also oddly a differential. And now you can see why in last class I said the value of a differential is 0. It's because of this fundamental definition of what is a derivative, what is the slope of a line at a single point. So that's why I did that, and that's what these bits actually mean. And I'm going to use that in a couple more proofs for chain rule and stuff like that. Okay, now knowing that this is this, I'm going to use this in a minute, and that these are slopes of a line and that this is sine, I want to remind you that initially this is a rising function, and the slope just happens to be 1 minus 1. So this derivative of sine starts out at 1, and at here, at pi halves, it will be 0. Because the function doesn't change. Here it's changing a lot, but negatively, and I have to do this to make it line up correctly. It's actually hard for me. And here it is not changing again, so we're here. And here it's again rising to a maximum. There we go. Okay, literally the definition of cosine. Okay, now you can see how you could have done that question, the question on the second quiz, number 2, when instead of giving you this, I gave you this, cosine. Now, the way, you're thinking like, oh, well, how could I have known that? Well, I just kind of thought you'd recognize it for what it was. That's how you could have known that. I did, because of the prerequisites, I thought you would be saturated with trigonometry. You're not, but that's why I'm covering it. So anyway, now, okay, so therefore what I can write, I will have these on the cheat sheet. You will need these, by the way. So the derivative of sine is cosine. Now, do this operation below it, and let's see, what do we get? Let's do the derivative of cosine. And just practice this sucker right here. Okay, so it's not changing at first, but then it's going downward to a maximum right here. Then it's not changing at this point. And then we're rising as fast as possible right here. and then we're not writing it all right there. Okay, so what I see from this is that the derivative of cosine is minus sine. It's a little different. Okay, now seriously, when I am doing calc questions and if I get stuck, I will literally draw this out to get myself unstuck if I'm at a test situation where I can't just Google it. Anyway, also the other bit of trig that you are going to run into in about a month is tangent, which is sine over cosine. The derivative is cotangent or something. Anyway, we'll cover that. We'll cover that in a little bit. Just to remind you about trig functions. Okay, so this is all fine and good. I know this is a little childish. Sorry about that. So let's up the notch a bit. So what I'm trying to do is walk you through that question 2 on the last quiz. Again, a lot of folks didn't even know how to begin. It's fine knowing that the derivative of sine is cosine. And yes, I did expect you to have that stored in your memory banks. I will have that as an identity on the test. But you've got to understand that I'm going to feed the function. Here, let me draw the sine function again. But you know that functions just aren't functions of x. So this is sine of x. Okay, but now let me do sine of 2 pi x. So this will be sine of 2 pi x. Okay, because I'm never going to just feed something just an x or a y or a z. Okay, so what happens here is it looks to me, now you got to fight your instinct sometimes. It looks to me like this ought to stretch it out because you're stretching the x. No, you're compressing the x. So before, this thing does a cycle at 2 pi, but this will do a cycle at 1 because it's multiplied by 2 pi. So this is going to come up, by the way. So what happens is this guy ends up being compressed. And I actually did, I'm not doing it. I'm already screwing this up. 1, 2, I've already screwed this up. It actually compresses it a lot, my bad. And I had to use a computer to draw this because I'm not good at this myself. It's actually pretty sharp. Here we go. It's like this. And now what I'm going to do is the derivative. Okay. Well, now you saw what I did. Let me simplify it. Sorry, it's not at my best right now. But anyway, okay, so this is sine of 2 pi. And now what I want to do is the derivative of this, because when you do all of these quantum questions, you're never going to have e to the x, you're never going to have sine x, you're going to have e to the blah blah x, you're going to have sine blah blah x. Okay, now if you get confused about how to walk your way out of this, without even remembering any calculus at all, you can just draw stuff and answer the question. And the way to do this is to note that if you start looking at the slope of the line versus x, you look at the slope of the line versus x. For one, I see the same periodicity in terms of up and down. So the derivative is, here, let me write this down. The derivative of sine 2 pi x, and of course this will be anything times x, so I'll call that kx. I'll call that in a second. I just want to make this more solid. The periodicity of the derivative has the periodicity of the function. I can see that just because it's still going up and down. Now, that's half of it. The other half of it is that because I've compressed the function, it slopes harder. That's my word for that. It slopes harder. It has the same motion in y over a shorter range of x. dy dx is a slope. Okay. Now it turns out that, we have a rise and then it stops, and the slope happens to be 2 pi. So again, the periodicity is the same. And I'm not drawing such a great job of that, but anyway, but the slope is magnified oddly by the interior, but 2 pi. Okay, so what about that? So therefore I conclude that the derivative of sine of 2 pi x is 2 pi cosine. Now remember, the derivative is cosine 2 pi x. We've already went over why it's cosine. The 2 pi is still there because the periodicity in the changing slope is the same. And the 2 pi accounts for the fact that you have the same rise over a shorter run. That's the definition of a slope. That's the definition of a bigger slope, and it happens to be 2 pi times that. Okay, now to do this more formally, and I can't emphasize enough, you're going to have a zillion of these in the next month. We have to cover the chain rule. So the way to do this is with the chain rule. And before I do that, I'm sorry about this, but a lot of folks are still struggling with derivatives of the nature x to the n. Now the power rule, I looked up the derivative, so the power rule gives us the formula for these derivatives, and it's all based on limits, and I don't want to write that down because it doesn't really matter. You just got to remember, you bring down the exponent and then subtract 1 from the top, and don't forget that if you have a constant times the function, you just bring that on the outside because it doesn't matter. Remember, it affects the slope, just like what I just drew affects the slope. There you go. Okay, so this is important to the chain rule. And so let me write out the chain rule and apply it to this bad boy right here. And then we're going to do exponentials. And exponentials are actually slightly, it's a little bit harder to prove, to give mathematical proofs of derivatives of exponentials. It takes a couple more steps. The end result is actually significantly easier. Okay, so chain rule here. Let me start the chain rule over here. Chain rule to solve the derivative of 2 pi x. Okay, the way this works is if you have y, so I'm going to say y is f of x. It's a little bit of a different mathematical language than I used before, but I'm not going to say y is f of x. I'm going to say y is f of u. If y was f of x, then I'd just be doing regular calculus. This is chain rule. Okay, now the important thing is that u is a function of x. So literally, I have a function of x. That's why this gets a little bit painful. Okay. Now, in the case I'm showing above, this is sine, and this is 2 pi x. Okay? Now notice I didn't give this an argument, right? Sine of what? You don't have to. That's why this is actually not so bad. All right, so the derivative is then based on just ratios. You can do it this way. The reason is that these cancels, just like a over b times b over c is a over c dy dx. All right, so it's equal to itself. Okay, now let's use the above right here. Okay, let's do this one first. This is the change in 2 pi x with respect to x. X to the 1 is now 1 times x to the 0, which is 1. The 2 pi comes out. Okay, so that's not bad. Let's do this guy here. Sorry, I didn't do such a good job there. All right, now remember I said I didn't give this an argument. This is the sine of u with respect to u. And so it's childishly easy. Just let it be childishly easy, because it is. And that, of course, is cosine u. Okay. So therefore, God, sorry, I'm not using the board so great. Change in y with respect to x, which is the change in sine 2 pi x with respect to x, is, I'm going to write this in reverse. I'm going to write 2 pi cosine of u, but u is, you got to remember to put that back in, cosine of 2 pi x. Ammo. There you go. That's how you do it. And I will have these formulas on the cheat sheet. Let's do another one. That's relevant to this class. As I have been babbling on about e to the I kx, let's do e to the I kx. Okay, so let's do what's the derivative of e to the I kx? How could you have known that one? Now, I'm going to cover why the derivatives of exponentials are exponentials. I'm going to cover that formally in a minute, but let's take it easy and let's apply this chain rule. Let's apply this right here. What I've got to do is identify the different parts. All right, go slow, go methodical. And so y is e to the u, and u is I kx. Okay? Now the next thing is that then the derivative is therefore dy, du, du, dx. Okay? Now I'm going to cover this in a minute, but the derivative of e to the u is e to the u, but remember u is I kx. The derivative of I kx with respect to x is I k. There you go. So these will get actually substantially harder. So I know this is a little bit childish, but it will get harder. So you may want to fall back on these formulas. Once you've done them enough, they will get kind of second nature. I tend to just shoot these out of my, I'm often talking and I'll just start saying what the derivatives are. I know that's kind of annoying. It's just like, you can't really turn it off. I'll try to slow down in the future. Let me also, you don't need to know this. Sorry, I'm not using the board so well today. You don't need to know this, but I wanted to just drill this into your head as much as possible. I'm going to prove to you why the derivative of e to the, I guess I said e to the u, right? I said the derivative of e to the u is e to the u. I want to prove why that is the case. And I think this is just something that it's not on a test, all right, but it's going to help a lot to know where things come from, even if you don't need to know that. Okay, so y, and I'll go back to the language of x as opposed to u's, which is a bit more familiar. Why is this true? Okay, now as I mentioned, to reinforce what I just said about what the definition of a derivative is, let's look at this as a limit of some change, some displacement in the function as it goes to 0. The limit of what? This is e to the x plus delta x minus e to the x. So you see it's a change in x over the change in y over the change in x. Okay, and this is equal to the limit. I'm just doing a little bit of algebra of e to the x, e to the delta x minus 1 over delta x. Okay, now since this thing is now effectively a constant, this is the thing that's changing. This is a constant. So what I can do is take it out of the limit. Again, don't worry about trying to memorize this. I just want you to get really familiar with what you do with exponentials, because you're going to be doing a zillion of these. Okay, so you get to this. There's just a little bit of algebra involved with this. And yeah, that's right. Now, here's the damnedest thing. It turns out, there's a couple more steps to this proof. It turns out, literally, the definition of an exponential is, you ask yourself, what's an exponential? Go look it up, put it into here, and this is all 1. Right? So it turns out exponentials, you think of these as being nature's ratio. You probably have heard that term before. Hopefully you have. Anyway, exponential growth, that's MBA. That's how your interest rises with time, compounded interest continuously. So nature follows exponentials. But literally the definition is in the form of a limit. that basically cancels this limit out and says that this is equal to 1. So therefore, the derivative of e to the x dx is e to the x times 1, which is e to the x. Anyway, I just want to be very rigorous and show you why that is. And let's see, I got one or two more examples. And again, I want to emphasize that I am doing examples of things you're going to see. Natural logs. Okay, now that I've introduced exponentials, then we're going to do natural logs. Oh wait, I think I have one more example. Am I missing an example? No, I'm not missing an example. Okay. So just remember the chain rule as it applies to exponentials. Exponentials are actually the easiest thing to do the chain rule on because of what I just said up there. The exponential always survives the operation. The exponential always sticks around after taking the derivative. The same thing will be true in an integral. I'm going to cover integrals as well. Okay, well let's cover natural logarithms. Okay, logs. And I'm going to prove to you something. Now, a lot of you got this wrong last semester, and it's going to come up not during quantum, it's going to come up in kinetics. Remember, we're going to end this class with kinetics. So I'm going to go over some things about natural logarithms, and I'm going to start with e to the actual y equals x. Anyway, blah, 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 just a bunch of letters. E to the y is equal to x. And I'm going to use this to make some proofs about natural logs, which you are going to need, not quite now, you needed it last semester, but you need it at the end of this class. Okay, if I write this, and therefore y is the natural log of x, and that's just a definition, hopefully that's familiar. If not, then there it is. Okay, now let's do the chain rule. Let's do e to the y, and let's change that with respect to x. Now the chain rule says do the derivative of the first guy, which doesn't change, and then we do the derivative of, technically, the argument of the exponential, which is this. All right, so derivative of the function times the derivative of the inside, essentially, right? That's the language you heard before. Now, since this is all equal to x, then this is equal to, then the derivative is equal to the derivative of x, which is equal to 1. All right, what's the point of this? Well, this thing is equal to x, and the change in y is equal to ln of x. I know this is kind of funky looking. I couldn't really think of a better way to do this. Okay, so therefore, let's see, x times the x times the change in the natural log of x with respect to x is equal to 1, and therefore the change in the natural log of x with respect to x is 1 over x. There you go. Now, if you need this, and you will when we get to kinetics on the cheat sheet, but now you know where it comes from, right? That's why I'm covering some of these things I don't need to cover. I want to make you ultra familiar, comfortable without, it's great when you don't need the cheat sheet, because then you're nailing it. And this is how I'm trying to get you to do that. Now, the reason this guy's important is, for one, when you're integrating, this formula comes up more when you're doing integrals than when you're doing derivatives. And this is something a lot of you got switched. A lot of you reversed this. You didn't take the derivative of natural log and got 1 over x. You were actually integrating it. Anyway, it's something I saw got confused a lot of times, but anyway, I'm coming up to that in a second. We're about to do integrals here in a minute. Natural logs, there you go. Let me do the product rule and some examples of that. I'll even prove the product rule, because that is going to happen, an unbelievable amount. So I'm going to do the product rule, I'm going to do a little bit of double derivatives, then we're going to do integration. I'm going to give you an example of every integral that you will solve as part of quantum mechanics. And also, when it comes to product rules, I'm going to do product rule right now. This is going to be important because we're going to go to 3 dimensions here shortly. And that means that you're going to have function times function times function. Function x, function y, function z. Product rule, product rule, product rule 3 times. So you've got to get this guy down. This is definitely terribly important. Okay, so the product rule goes like this. I'm going to write it down, then I'm going to put it. SOB, there you are. So the product rule. Chain rule is probably more important. These are probably equally important. Chain rule is a little bit harder, but this is when you have 2 functions multiplied. It goes like this: derivative of 1 times the unmolested, is the technical proper word, function of the other, and then you vice versa that. I actually forgot where this comes from. I think this is actually kind of interesting. And this will also help solidify some of the mathematical terminology and language I use. Here's the derivation. And this is, what is the change of fx times g of x? Okay, what is the change in these functions multiplied? Now, using that definition of derivative, which actually I could use to define partials, I was able to do this. So this will be f of x plus some delta x, or delta x. There's a limit, goes to 0. I'm not going to write that down. It doesn't matter for the purposes of this example. Okay, so these are the functions advanced a little bit to the right, minus where they were at. So this is the change in the rise. I don't need to divide by the change in the run. And using some of the language that you actually had last semester, and again, I should have done this last semester, I'm sorry about that. You can express this like this. It's perfectly legit to do it this way. To say that the function, having been moved a little bit to the right, is what it used to be, plus some small change, that is totally fine. Minus fg. Again, I'm just using, technically this is Leibniz notation from calculus. Anyway, I also want to do this so that you get familiar with some of the notation. Okay, now notice, FOIL, f of g minus f of g, right? So that's gone. What you're left with is df times g plus dg times f. Okay, and this is the change in fg. Notice that if I make it a derivative, there you go. Which is the same thing as up there, exactly the same thing. So that's where it comes from. And again, on the cheat sheet, and let's see, where else do I have? Okay, let's do one that you actually have on the present homework. You actually have it on the last homework. You're going to be doing this one a bunch of times. And again, it would be best if you could do it in your head. Practice, that's why I have as many homeworks as I have. Okay, the first derivative is x to the 1, so that's x to the 0, which is 1. So this guy doesn't do anything. Then I don't mess with the x. I take the derivative of the exponential, which is chain rule, and there you go. That's it. So let me actually point out that if this was an eigenvalue equation, if this was an operator, if the operator was the derivative, like the momentum operator, and this was the wave function, it fails. It fails because of this term right here. If I took the derivative of the wave function and the wave function came back times a constant, that would be valid. It is invalid because of that term. Anyway, just to connect it back to class and your homework. Let's see. What do I want to do? All right, yeah. So for all of our class, for the remainder of the quantum mechanics, this incorporates everything we've done. We've got product rule, we've got chain rule right here. There you go. That's 99% of it. Derivative of sine, cosine, derivative of cosine minus sine. You got that. Also, double derivatives. I just want to point out that, and look, 5 or 6 of you got this wrong. A double derivative is literally a derivative done twice. Now, the notation is what tripped up a lot of you. Notice where the 2's are. Here, I'll apply it to a function. It makes it a little bit easier to read. I'll apply it to a function. The 2 goes here for a reason, because if you put it here, and a lot of you got this, a lot of you thought this was what was happening. This is the function squared. No, that doesn't make sense. I would just tell you to take the derivative of the function squared. This means do the derivative and do it again. So, again, look out for that. Again, it did trip up a lot of you folks, so don't do that. It's a simple one. All right, and then last 10 minutes, let's go over integration. And the videos I sent do a good job of doing this very formally. But I'm going to show you how I do it. So I hopefully pushed you enough that you're going to watch the videos. Because I don't think what I'm doing is going to be enough to make this stick. I hope it's a step in the right direction. But I want you to watch the videos to augment. But I'm going to show you integration like I do it in my head, because I don't know, it works for me. And I can explain it best. I'm trying to think of how you spell integration. So I tend to do integrals very differently than they're formally taught. I tend to do derivatives backward. And again, it works for me really well. And the fact that you're going to be integrating exponentials, it's going to work doubly well. I think this way of explaining integration is extremely good for exponentials because they survive differentiation. Okay, so integrals that go backward. Okay, let me do this. Let me be a little bit more formal before I show you the loosey-goosey way to do this. Let me just write down the derivative of the natural log of x. It's 1 over x. Okay. Now, this is how I could define an integral. It's also a way to solve it, right? So basically, knowing how something is defined would go a long way into solving it, right? Okay, so now what I'm going to do is, knowing that these partials can be juggled around like just little ratios, and remember how I've said a zillion times that partials, now that I've done this, I've set up an integral, and so now I'm going to do this. I'm going to do this, and I'm not going to worry about definite. These are indefinite integrals. Let's not worry about that distinction. Not now. This ends up being natural log of x, and I'm going to leave this alone. Why am I leaving this alone? Because this is the exam. This is a very common kinetics equation. You're not going to see it in quantum, but you're going to see it at the end of class, the kinetics. You will see this again. I've asked you to integrate 1 over x. The answer is natural log. Why? I just showed you why. That's why. Okay. This is one of the ones you kind of have to have memorized. You might recall the first Friday in class last semester, I told you this. Again, this is the thing, you guys, you got the integrals and derivatives completely mixed up for the most part. Don't do that. This is how you get out of it. And anyway, so let me show you a couple more examples, and then I'm going to show you how to just kind of do it in your head. Let me see here. Where am I? What am I doing? Yeah, let's do this. Now here, let's see. I've got a couple of sines and cosines, and I think you're going to end with that. Yeah. So let me show you actually my way of doing this. Okay. So whenever I run into an integral, and I'll give the 3 or 4 examples of how my broken head works. Anytime I see an integral, I see this, okay, here's about, make this as easy as possible. I know that integrals basically undo derivatives, so I start asking myself, the derivative, okay, so this is separate, all right, this is the question, this is what goes on in my head. The derivative of what gives me x, right? And this is the answer. And again, forget definite, forget limits. Let's not worry about that. Okay, so now, what is it? Knowing the product rule, I know that I'm going to have an x squared, right? Now, I know this because when I subtract 1 from the exponent, I've got x to the 1, I've got x to the 1. All right, so I know I'm halfway there. That's correct. I am halfway there, x squared. All right, now I double check it. Derivative of x squared is 2x, which is not x. I don't have the answer. Okay, it's clear what to do. Divide by 2. Divide by 2. Now it's equal to x. There you go. So the integral of x is x squared over 2. Now you can apply limits and all that, but I'm not going to cover that. Again, childishly simple, but personally, this is what goes on in my head when I do this. Now, why am I talking about that? You are going to be integrating e to the ikx a bunch. And this way of thinking, I know maybe a lot of you, this isn't going to work. It does work for me. But the reason I want to cover this, even though this is kind of not the right way to do it, in those videos I sent have more of a formal, more formal in terms of like, this is how you do this exactly without any approximations or taking any limits and all this jazz. It's very useful because we're going to be doing lots and lots and lots of exponentials. So let me do an exponential. Okay, we're going to be integrating e to the ikx a gazillion times. Okay, now I asked myself the derivative. Now here's the thing. Here's the thing. The reason I like thinking this way is that I know integrals survive the differential. Remember, I'm going backward. In terms of solving an integral, I'm doing a derivative backward. I know that the answer has e to the ikx. Because remember, I'm trying to find the thing, the derivative of which is this. That thing is the answer. Now I know that the derivative that gives me this has to contain this. I know that the answer looks like this. I'm halfway there, right? Halfway there, because I know that it's e to the ikx has to be there. Okay. So then the second part is I do the derivative in my head, and chain rule, right? I get this. This is not correct. The derivative of what gives me e to the ikx? Well, this isn't it because it's not e to the ikx. Divide by ik. Right, divide by ik. I know this is very simple. Ik. And that is equal to e to the ikx. There you go. I can't emphasize this enough. I think this is a really good way to do these, and you're going to be doing them a very, very, very large amount. You even have a question on your present homework where you have to do this. Okay, now you are also going to have to integrate sines and cosines a lot. That has to do with the fact that we're going to be doing things in r theta phi. Guess what? Sine theta, sine phi, cosine theta, cosine phi, integrate. You're going to do this a lot. So let me cover those. And this is, I'm going to go back to that first way of expressing integrals. But how do you define integrals to begin with? I guarantee you this will be on, maybe not this first test, it is absolutely going to be on the second test. So let me make sure that you can nail it without having to look at any cheat sheet. You let your gut tell you the answer because you know it. Write it down, look at the cheat sheet, see that that equation is there. You nailed it, you move on to the harder one. That's how you get A's, all right? So, I've asked you to integrate, okay, this is subtle. This is why this is actually a little hard. And I actually forgot this myself. I'm going to ask you the integral of cosine. Let me walk you through how I define the integral of cosine to begin with. And again, it's a derivative run backward. I know that sine, the derivative of sine is cosine. Remember, I've asked, again, I'm not going to write it down, but the problem is, what is the integral of cosine? I got to remember the derivative of what is equal to the thing I'm integrating. So yeah, I've already got the answer, but hold on. Okay, we've already covered this, right? Okay, now I do the separation, because I can, because this is like juggling. Okay, now I integrate. And this again, by definition, this is just sine x. There you go. The integral of cosine is sine. Now, actually, the reason I'm walking you through this, because when I did this off the top of my head, as I was writing my notes in 3 hours before class, I actually wrote minus sine. Right? Because the derivative of cosine is minus sine. No, I just lost a point. Right? It is not minus, it's plus, for all the reasons I just walked you through. It does get a little bit subtle, but here's how you do it. Let's see, do I have another example? Well, I won't do this, but I just want to point out that, well, here's one more example. And again, I can't emphasize this enough, this is on the test. It's not just remembering this stuff, there's a problem that you have to do this. Okay, we already said that the derivative of cosine is minus sine, and I can already just jump to the chase. The integral of the change in cosine is just cosine, which therefore is the integral minus the integral of sine. So therefore, you see, I know I'm not doing the greatest job here, but I'm kind of doing this off the flow of my head, so you're kind of seeing me think out loud. Therefore, the integral of sine x is not cosine, it's minus cosine. Again, my gut would have gotten the minus sign wrong because I would have been doing a common mistake. I wouldn't have been integrating sine, I would have been taking the differential. If I took the differential as sine, I got cosine, but this is not. This is the antiderivative, it's minus cosine. Let's see, and last bit, let me give one last example because, and then that'll be it, and I'm out of time anyway. Last example is because I don't give things that are just x's. They have something inside of them, like k's and 2 pi's. Let's do this. Okay, now I've already gone over many times that the answer is 2 pi, the chain rule. Okay, so then the integral of the change in sign, 2 pi x, is of course sine of 2 pi x, which is equal to the integral of, here I'm just going to go ahead and divide by 2 pi, cosine 2 pi x. So on the exam, what's the integral of cosine 2 pi x? Sine over 2 pi. There you go, that's the answer. All right, folks.